Hi, I'm Johnny from the Speaker Building Garage, and today I would like to make a short video documenting the process that we go through to design and build top quality speaker boxes. There's a whole lot of things that go into it, but some of the most important things I can demonstrate in this video. It's going to be a several part video, so let's get right to it. Over here, the very first thing that I usually do is I go into a catalog like this, and this particular thing is Parts Plus. They have a catalog. And you can see different speakers. So you have like a tweeter here, you have a woofer there, and you can get mid-range. There's different sizes depending on what you want to use it for. And so I'll look at these, and you can look through like pages of this. Like if I turn the page, you can see there's more over here. If I go back this way, there's more. See, there's hundreds of these things they sell. And in order to figure out which one I want to even put together with another one in a box, I have to go online. So before you purchase any one of these, you can look at documents like this, for example. These documents give you the electrical and mechanical parameters of the device in question. They also describe the technical dimensions, like how wide and how deep it is, so you know how to fit it into the box. They'll give you a frequency response diagram, which basically tells you how it plays the sound, what it will sound like in a certain size box. They tell you what size box they tested it in. They give you information over here. So this is kind of like technical. It's like a PDF file you can get on the internet for every single one of these speakers right here before you buy it. So you don't have to like buy a speaker blind. It's like, I don't know how this is going to work or whatever. You automatically know, because before you decide to purchase any one of those speakers on there, there's a document you can look at. So what I do, and what most acoustic engineers or guys that work for companies that design speakers and boxes and systems like that, they have to pick parts, decide which parts they're going to put together in a box based on their experience and reading technical information off of these papers, which I just demonstrated. And then once you have an educated idea about how you can integrate these things together into a system, then the next process is you basically go in the catalog over here, and you look through it, and you look through the final information you want, the power handling, the specifications. You double check everything. Let's say I wanted to pick this one, so I will order this one, $110. Then I would have picked, let's say, this dome mid-range, and I would have picked this for $33. It's just an example. And then I would pick a tweeter. So I would order those, and they would be UPS shipped to the garage here. And once I get them, I can start building a prototype box. So the system is basically, to sum up, a very simple methodology that we use here. We first decide what speakers. We don't build a box and think about the speakers. We first look at what speakers there are available and figure out which ones we can put together in a box and how they might sound, because we don't like have them sent here, try it out, build the box, and it's like it doesn't work, send them back. We don't go through that hassle. I have to make the decision before I purchase, and this is hundreds of dollars worth of equipment, whether it's going to probably work together in a box that I can imagine in my head. Like I see this going into this or that size box. Will it work? So I have to figure out whether they will work before I purchase them based on technical information in these documents. And every single speaker that's for sale has all the documents, so I can read the graphs, I can read the technical parameters, the mechanical, electrical characteristics, etc. And it will tell me information about what I need to do, what I need to purchase, etc. And one other thing is, for example, on tweeters right here, they give you information like as you move from side to side, like you go from left to right, how strong the sound will die off. So it's like a lobe plot here, a polar response. So right in front of the speaker, obviously it's louder. As you get so many degrees left or right, you can see the line starts to go inward, so many decibels. And so you can guide yourself with polar response graphs, frequency response graphs like this one, impedance response, which is the resistance of the voice coil mounted in the box. You see there's a bump there because of the resonant frequency of the driver. And there's all kinds of what they call field small parameters, like how much the cone vibrates, how much is the farthest distance the cone can move in or out, different things about how the resonant properties of it are. There's all kinds of information there. Every single electrical mechanical parameter of the speaker that affects how it behaves inside of an enclosed box is stated on that paper. So an engineer like myself that understands how these things work and whether they will work in a certain box to read the paperwork, read the documents, and figure out, will this speaker work in the box that prototype box that we envision putting it in? And then we put the speakers into the box and we create the product. So that's all for part one, the initial phase of picking the parts and figuring out if they go in the box. In the next segment, part two, we'll talk about how we build the box. We'll show you some of the little things we use, some of the little baffle boards and test boxes, some of the tools, and the general way in which you put together a box and then make it so we have a prototype that we can start experimenting with and perfecting until we have a final product. I'm Johnny from the Speaker Building Garage. That's it for part one. So hi, I'm Johnny from the Speaker Building Garage. This is part two. We're going to show you a little bit about how we build boxes here, so this should be pretty interesting. So anyways, here's an example of the front of a box. Now I don't have an entire box here because we'll be looking at the box later in the testing room, which is inside of a vehicle. But I'll show you how a box looks. This is like a prototype panel for the front of the box. So it's like a woofer, a mid-range, and two tweeters. So this is we cut out like a baffle board and where you mount the parts, and you can use this as a test board in the final location if you want to get an idea for how they acoustically kind of fit. Another example for a built box would be this little test box right here. It's a small 2-liter box that we tested the 6-inch mid-range in from the Italian company 18 Sound. It's a really small mid-range, and we did a lot of testing in this small box here, and we have a box like this built into the bigger box in our final product. So what we do is, like, if we make a box, and this applies to any box, the little one or the big one, we end up putting this material in here which looks like cotton candy. What this is called acoustic stuff. It's made from polyfibers, and it absorbs the sound that comes out of the back of the speaker. Because here's an example I'll give you right now to make it easy. You have a speaker and you've got the diaphragm right here, and that's what vibrates. So sound radiates out of the surface, like anything you hit or touch that vibrates, it makes sound. So when the coil vibrates the surface because it's near a magnet and the electric signal makes it move, it vibrates this whole thing. This is a diaphragm. You touch it, you can hear it making sound too, because it's all it is a paper diaphragm. When it vibrates, sound waves come out of the front and they come out of the back, and the back part faces inside the box. So what happens is the sound coming out of the back is going opposite the way the sound in the front is, because the wave that comes out front goes forward, the one that comes out of back goes backwards. So they're out of phase. In other words, they're not going together. They're pushing and pulling in opposite ways. So the sound that comes out of the back goes into the box, bounces off the walls, and makes echo, and that hits the back of the diaphragm and pollutes the sound. So in order to make it sound good, we only want to hear the sound that comes off the front surface, not the sound that comes off the back surface in the box. So we put this material which absorbs sound waves in the box, and it absorbs the sound that's coming out of the back of the speaker. So it's like this. You're only hearing the sound coming off the front, and that's why we use a sound damping stuffing and put it inside of the boxes. You always have to do that, or else you hear echoes and other strange sounds coming from inside the box. So that's kind of how that works. And so when you build a box, it's kind of simple. We use something like, I'll give an example, MDF fiber board. It's a compressed board made of like sawdust, and it's bonded together with glue, and they compress it at a factory. We use 3/4, that's quarter there. We use actually this thickness right here. So it's like a thicker piece of board like this. It's 3/4 inch. And the idea is we join the boards together like this. We do a joint like that. And then what we do is we drill holes in the board, and we use glue. So the glue and screws actually. So when we put the pieces together, we'll put glue on the joint, press the board together, and then use screws to tighten it down, and it'll solidify and get hard in that position. Now it's a solid connection. And so all you have to do is cut out the front. You have to cut out like the sides, the top to bottom, the left to right, and the back. And in the back, you cut out a little place to put terminals like this, so you can connect the wires to it. So you have a little terminal plate, and you put the terminals in the back, so you hook the negative and positive wire from the amplifier or the crossover, which almost always you have to have. So in our case, we have 3 of these. One of these goes to the big speaker, one goes to the little speaker, and one goes to the small speaker, and the wires inside the box are connected right to the wires on the speaker, and all that occurs inside the box. So there's a little bit of wiring that has to happen inside the box. And these are some of the tools we use. I mean, we have all kinds of saws and drills. We have hole saws to cut out circular holes. I'll show an example what a hole saw is. To cut out the hole, like for the pipe port, for the base hole, you use a big hole saw like this. So you hook it to an electric drill, it spins around, cuts a circular hole in the wood, and then you can install something like a port pipe like this over here as an example, and you would have like the thing inside the hole. And the idea with that is that you have a volume of air inside the box. It's a certain amount of air, and there's a certain amount of air inside this pipe. It has a certain resonant frequency, like a bottle. You blow over it and it resonates at a certain tone. and that's called a ported box. So my boxes are ported, meaning they have a pipe, and you'll see them later on when we show you the final box inside the testing location, that there's 2 tweeters in mid-range, and the design also has these 2 pipes where the air can come out from inside the box, and that causes it to resonate, and that increases the bass. It changes the bass parameter. And so we build ported boxes like that. You know, you got 2 portholes in the side. They're glued and screwed together. We cut the holes with a circular saw, or we use a starter point drill, and then we use a small jigsaw with a little blade to kind of guide it and cut a shaped hole for the bigger holes. And that's how we get these larger holes like that. And that's all you do. You build the box, you glue it and screw it together, you put the stuffing inside, make sure that's in there. Then you go ahead and you take the speakers and you screw them onto the surface after you've wired all the internal connections from the speaker terminals to the terminal in the back, where you're going to hook the wires on the back of the box, and you have a complete box. Now your box is done, and the only thing left to do after you've built the box, then you have to tune it, meaning you have to adjust the amount of stuffing, you have to adjust the crossover circuit, which is made from these different components to adjust the frequency response of the speaker, and that is the part that's called tuning. You adjust the stuffing in the box to change the tone of the sound, and you adjust the filters that control how much of the sound of different frequencies goes into each speaker, how they work together to create the final panorama of sound, where you hear it coming from, the position of it, all the perception of the high and the low and everything. It's all related to that. It's all related to how the speakers behave in the acoustics of the box, how they interact with the physical environment where they're placed, and the kind of components you put into the crossover circuit. And all that has to be done by ear. So there's an entire procedure of, you build a prototype box, then you make a software test after you get some measurements, and then you tweak your circuit and your crossover to adjust the frequency response and try to get the speakers to knit together sonically in the particular place where you're listening to them to get the proper kind of sound. So in the next video, I'll talk about how a crossover circuit is built and designed, and that will get a little bit more into that part, the crossover part, the filter part. This is the part that controls the way the speakers sound, how they tune in a particular location. I'm Johnny from the Speaker Building Garage. That's it for part 2. Hi, I'm Johnny from the Speaker Building Garage, and this is part 3. In part 3, we're going to talk about crossover circuits. So the crossover circuit is like several electrical filters that alter the signal in a certain way and control what frequencies go to what speaker. And so there's a filter for each speaker. So if you have 2 speakers in your design, a big one and a little one, so the big one produces the lower frequencies, and after a certain point it transitions into the little one and it continues to produce the higher ones. That's a 2-way design. If you produce a 3-way design, you can produce as many ways as you want, but the most common ones in the industry, you'll rarely ever get more than 3-way, and one speaker never does it. So you always have to have at least 2, a big speaker and a small speaker, like this would be. The big one produces up from the low frequencies as you start. As it gets higher, at some point this one stops producing and they start coming out of this one, so they share. So the sound spectrum, like from the bottom to the top, you divide it. The lower half will be done by this speaker and the higher half will be done by this one. That's a 2-way. The only difference between that and a 3-way design is that instead of having 2 speakers, you have a big one to produce the lower frequencies, and then you have a small one to produce the high frequencies, but you have a range in between that's produced by a middle-sized one. Now those are a little more effective because it divides the work over more speakers, and they specialize so each one sounds better because you're not using it for such a wide range of frequencies. The design I'm working on, the JB100, which I show you the baffle board for, and we'll see later on inside the vehicle, my revolutionary new design is a 3-way speaker. It's not a 2-way. Because I like to have a 3-way, because it's a dedicated speaker for the mid-range, which is that sensitive range like between 1 and 5 kilohertz, where most of the audio information is that tells us where things are located, the clarity. You close your eyes, you can hear exactly what direction it's coming from. Your ears learn that information by listening to cues from the mid-range frequency and the phase relationships and the frequency balance of the spectral energy within that frequency band. That's what gives speech intelligibility. It's called the speech intelligibility range, and that's what gives sound the ability to sound clear outdoors at long distances. So that's a very critical range. So instead of me dividing the sound into a 2-way, and if you do really well, QSC, for example, has their K12 series. They did a really good job of using a horn on the top and a woofer, and they blended them around 1700 kilohertz, and it sounds really clear. For me personally, I like to do it even a little bit higher level by using a 3-way with a dedicated mid-range. And so let's get right into how the crossover circuit works. So a crossover circuit is an electrical filter. We already talked before about inductance, capacitance, and resistance. So an inductor looks like this. This is an inductor. Basically all it is a coil of wire. What that means is it's a long piece of wire that might be really, really long. And then you just wrap it around and around and around and around like that. So it's like a coil. It's all in the same place. So any piece of wire, as you probably are aware because we've already did a video about this, over the whole length of it produces a magnetic field when you move a current through it. But it's all along down the wire. It's not in one place. It's not concentrated. When you take the wire and wind it in a circle like this, it takes many feet of wire and puts it in a tiny area, and it concentrates the magnetic force that's produced when you put a current of electricity moving through this wire. So what happens, this is electromagnet. If I apply a negative and positive voltage like a battery, it'll make a magnetic field and it'll pull a magnet or a piece of metal that's ferrous toward it. Or if the magnet has the same polarity, it'll push it away. So it'll interact with magnets. So what we use these for is they alter the signal. So what that means is if you put an electric signal through here and it goes in one direction and it doesn't change the direction it's moving, or there's no movement, it creates a magnetic field, it just stays one way. It doesn't generate any voltage here. But if you apply an electrical voltage to these two wires and a current goes through this coil of wire, what's going to happen is if you change that voltage and the current moves, the magnetic field that it produces will grow or shrink. And every time there's a change in the magnetic field, it will generate another voltage in this wire that's going in the other direction. So at low frequencies, the vibrations go back and forth slower, like this, let's say. So if something's vibrating slowly like this, it's not moving that fast. As the frequency increases, each time it moves back and forth, it has to accelerate faster. So at higher frequencies, obviously the voltage changes polarity faster in an audio signal, and so the current rises from 0 to plus to minus much quicker, and so it creates a much stronger magnetic field each time it moves. So what happens at a certain point as the frequency goes up and the changes in voltage become so fast that it starts generating a very strong reverse voltage, what happens is every time the voltage pushes this way, the one it creates inside the wire pushes back and blocks it. So at some point it starts to actually block the signal from going through as the frequency, as it gets higher, it starts blocking it. The point at which it starts to block it is determined by how much magnetic force it has measured in millihenries. And that's what inductors are used for. They're filters. They pass direct current perfect, deep bass, but as the tone rises higher, it starts to block it. And at a certain point, if you see it on a graph, it becomes a curve and it just starts to drop. Now I'll give you an example of what a curve would look like. You can say this is the point right here. The sound's going up and the tone goes up, and at some point it starts to just fall. See, it's falling. That's because it hit the limit there, and inductance value starts to block the energy from going through. Capacitor is exactly the opposite, and that causes a phase change. In other words, what that means is the voltage wave is like, it's a wave pattern, and I could probably get a pen and draw it on a piece of paper here. If I were to draw it on a piece of paper, let's say on the back of this piece of paper, you have a wave like this, and what happens is the wave shifts. So what happens is with the inductance, the wave is no longer, when it rises and you start to get more inductance, when the voltage rises, the current doesn't follow it. So the current lags behind. So a simple analogy for that would be, let's say I move something that has weight, like something, an object that has physical weight. I'll move this out of the way. That's a trip right there. Let's say I move this object right here, and I start moving this object, and this object, like if they move together, see how they're moving together? This one here is the voltage, it's pushing the current. As soon as it starts to push, the current starts moving. It follows it like that. That's what resistance does. So a resistor just controls how much, but it doesn't change when the current responds to the motivating force. So it goes up, it goes down, there's nothing going. As soon as you start having a motivating force, then what's going through starts moving. So it's like when you push an object, it starts moving immediately following the force you're pushing with. An inductor slows it down. So what happens is when it gets to that point where it starts to affect the frequency, where the changes are so fast that it makes enough magnetic field to create an impediment, a reverse impediment, starts blocking it. When the voltage rises and starts pushing, the current doesn't start moving. It lags behind it. So it's like you start walking down the sidewalk and the person behind you starts walking a few minutes and they're always behind you. It's that kind of thing. So the voltage is moving and the current is following behind it, but it's not at the same time. See that? It's following behind, it's lagging. And then because they're not in the same time and space, voltage multiplied by current creates the power. So if the current does not follow the voltage and there's a mismatch, it creates a resistance or an impedance, and that's the reason why as the frequency rises, the inductor starts to impede it and you start hearing less. And so you can shape the amount of tone going through and say at this point I want it to start declining, and how it declines and the angle at which it declines depends on the value of the inductor. Now back to capacitor, the second part. Capacitor is the obvious. It's two plates, like it looks like it's inside of this, it's like a roll of toilet paper. Two plates of metal film with an insulator in between, and you just roll it up into a roll. One plate is connected to this wire and one to that. When you apply a voltage across these terminals, it charges the plates because they're close to each other, but they don't have direct contact, and the electric field produced by each plate attracts the at more or less electrons from the error plate and keeps them charged. So it stays charged like a little battery. If you touch the wires together, it'll short and discharge. So basically a condenser or a capacitor is like a small battery you can charge with just a small charge. It takes a certain amount of time to charge up to full charge, and then it can't take any more charge. So it is similar like a battery. Now the thing about the capacitors, when you place it into a circuit in series with a speaker, so let's say the electricity has to go through here before it gets into the speaker. When it goes through here, there'll be no voltage on here at the beginning because it's charging up. And it's receiving a current that's going through it to charge the plates. When the plates become charged, the voltage across it rises, and now you have voltage. But you never have voltage and current at the same time. The current happens before the voltage, and the inductor was the other way around. So the capacitor does the opposite. It lets high frequencies go through, but it blocks the low frequencies. And the low frequencies can't go through because of that. So what happens is the frequency is really high and it starts to go lower, then it starts to impede it. So capacitors are the exact opposite of an inductor. An inductor, as the frequency rises, it starts to decline. With a capacitor, as the frequency rises, it starts to open up and then it lets it go through. So you use those two different components to create crossover circuits, and that's how we do it. We use those in our basic designs here at the Speaker Building Garage. This is Johnny from the Speaker Building Garage, and this is part 2. Hey, it's Johnny again from the Speaker Building Garage. So anyways, I gave the basic procedure for building a crossover, how the inductors and capacitors, and an introduction. Now I'm going to do a small follow-up to that as part of the same part. I'm just going to continue with that in another separate video. I'm going to talk a little bit about how we design, how we set the circuit configuration up, and how we do it with software. So I'll make it brief so it doesn't get too long. So like we did in the previous video, we talked about inductors and how they work. We know how capacitors work. These are resistors. They just resist. They don't alter the signal in any way. So they don't favor one frequency over another. They treat all frequencies the same. So you're just using the balanced levels of things. So this basically here lets highs through and blocks lows. This lets lows through and blocks highs. This is a low pass filter. This is a high pass filter. And this would be an all pass. It just controls level. It doesn't actually favor frequencies over the other. So that's what we do to build crossovers. So a typical crossover design is by order. So you have one component as first order. So you have a circuit where electricity goes through this coil to get to the speaker and make a complete circuit. There's one component in the circuit path that's called a first order crossover. If you want to make it a filter that just lets bass through, you put a coil. If you want a filter that just lets treble through, you use a capacitor. If you put them together so it goes through both of them, it creates a band pass. So this one here blocks the low end, that blocks the high end, and let a range go through. And so first order is you have one component. When you put one component in series and then it goes through another one to ground in parallel, so the first component is in series and the second one's in parallel, you have a second order. So every time you add a component, you start with one in series, then you put one from that point to ground in parallel, then you do another one in series, and every time you add a component, it adds an order. So the component, either this one or that one, coil or capacitor, will produce a difference where the sound pressure level and the voltage will drop 6 decibels per octave. That means every time the frequency doubles, there's 6 decibels less. That means the voltage is half. That's how much the change is as this makes it go down, like we talked about earlier. Every time you add a component, you add 6 decibels per octave. So if you want a filter that reduces your level at 12 decibels per octave, which is a much more sharp filter, it rolls off and declines much more quickly, it turns it off faster, you put 2 components. If you add a third one after that, the 2, now you have 3. This one, and that one, now it's 18, and so on. So every time you add one, first you do one in series, then parallel, then the next one they alternate this series, then parallel, then series, and each time you add a component, whatever the last one does, you do the opposite. You start with series, then you do parallel, then you do series, then you do parallel, and every time you add a component, you add 6 more decibels of change. So the simplest one is 6 decibels per octave. It gradually turns it off. As you add more, it becomes more steep, so it turns off much more faster. So you can control the angle of the curve depending on how you arrange these in the filter. So what we do to give us an idea is we start with our knowledge of this, and then we build sample things. So we take the frequency response diagrams from the manufacturer and we put them into the software here. And so what this software does is it allows us to look at the mid-range, for example. You choose which capacitor and coil are going to go. This is the capacitor here, and that is the coil, and you show what value you want, and it'll show how it will affect. So I'll show you the 3 speakers. This is the sample for the mid-range, this is for the tweeter crossover, and this is for the bass. And the blue line is the bass, the pink one in the middle is the mid-range, and the red one's a tweeter, and it shows how the 3 different lines interact. Now what happens is the place where the lines cross, where you see the 2 lines crossing, that's where they share the sound. Because the sound that's in one speaker, like let's say you have the sound in the bass speaker, as the tone rises, it gradually starts going down. You see the blue line going down. At that same time, the mid-range speaker is starting to get louder. And there's a certain point where they're producing the same sound pressure level, and if they are exactly in phase, that means the 2 waves line up, so the peak of the wave lines up with the other one, it'll produce a 6 decibel difference. So this program here, it mathematically adds them together, and the black line shows you that when you put them together at a certain point in relation to the drivers, and you pick the point where you're going to measure from, what relationship it has angle-wise and distance-wise from the acoustic center of each speaker, that will show you what, when they blend together, it's like you see the blue and pink line, when they blend at this point, they'll make the black line. So at every point, the colored lines blend to make a final black line, and that's a summation. So obviously, the woofer and the mid-range here, they add together and they both produce a sound. They share the responsibility, and the final sound of them mixing together is the level of the black line. And so what we can do is we can look in here, and let's say I were to adjust the level of, this is a second order. That L2 is the millihenry of the inductor, and the second leg to ground is the capacitor there, which is 11.20 microfarads. Now, if I go in here and I change that value, I put the mouse on it, you'll see the blue line change, and the black line will change because that the value of the sound it produces is going to change also. See what happens? As I put the capacitor more capacitance, it filter it more steeply, and as it goes down, it makes a dip in the sound. See the big dip in the black line? So now it's strong here and weak there. So you can see in the software how it's going to affect the sound. This is a relatively accurate simulation as long as your graphs are relatively accurate to begin with. As I reduce it, it lets more mid-range through, and as it lets more sound through here, it adds to the pink one, and the black line goes up because they make more sound because they're combining together even more strong in this particular part of the sound spectrum. So using this piece of software here, you create your simulations. You take your frequency response graphs for what the spectral distribution of tones are going to be for each speaker, and when they blend together, like the sounds from each one blends, what is the overall sound that's going to be produced? And that region where they share is how, at the point where the lines cross, they share the responsibility equally to make the sound. As it goes higher, the woofer makes less and the mid-range makes more, but that entire area where where the 2 lines cross is called the crossover region. And depending on the factors of how the phase is, because the inductor makes the phase shift back, and the capacitor makes it shift forward. So an inductor is like, I'll give you an example about phase shift. You have a loudspeaker like this, right? The acoustic center of a loudspeaker is placed right here. It's the farthest back place in the cone. You see where my finger's at right there? This is called the acoustic center of the loudspeaker. So if I have this loudspeaker right here, you see how they're like this? This one here, the front of the diaphragm is farther to the front than this one is. See how that one's deeper, it goes farther back? The sound from, if they make the same sound, the sound from this one is going to get to me before that one, because this one's farther back, this one's more to the front. So here's a plane like this, you can see in the camera. We're at an angle. See how these are lined up in the same plane vertically? And let's say this person's listening to this over that way. If I move this speaker this way, the sound from this one's going to get there before this one, because now it's closer, because sound travels at the same speed no matter which one it comes from. If I move this little one farther back, the sound from this one's going to get to there first now. So depending on how far back they are in the relationship between the two of them, you line them up depending on where you want them, farther back, farther forward. Usually they're on a board, but you can also put them farther back depending on where to load it into a horn that amplifies the sound or not. And this alignment in this axis, where one's closer or farther from the listener, which depending on how close or far they are from your ears, you sit in a certain position and they're behind your head or in front of your head, one's closer than the other, and when that happens, the waves don't line up the same way. They line up, either they line up where they're in phase, or they're out, or the phase starts to shift. And so when you have these kind of situations where the speaker is farther back or it's farther forward like that, it causes a phase shift. The electrical equivalent is the inductor. When you put an inductor, it makes a phase lag, meaning the current lags the voltage. So if you put an inductor in series with the speaker, what ends up happening, it has the same effect as if though you move it physically back. It does the same thing to sound. In other words, it makes a retardation of the sound, so it lags. So if this speaker here has a coil in the circuit, and they put them lined up like this, it'll make it sound like it's back here. If you put a capacitor, it has the opposite effect. It makes it sound like you moved it forward. So if the speakers already have a difference in the box, like where they're at, where one's farther back or one's farther forward, and you have to use these filters in order to make the crossover, it's going to make it seem like it's this way or that way, and there's going to be phase shifts. And so sometimes you have to reverse the wiring on one if it's like 180 degrees out of phase and do little things like that. But those are things you deal with in the position of each speaker relative to the listening ear, and the components you use, how they affect the phase of the current in relation to the voltage of the audio signal. And those are the two things I want to go over. Those are the simple things of the design there. And here's how this part works. Here we basically look at how this is going to sum up. We tell it where our ear is going to be. We give it the exact geometry of the box right here. For example, up here, there's a place at the top here where I've given the exact geometry. I've told it where they are, how many millimeters it is from each, like this one's farther back, this one's farther forward, and it gives the exact offsets. You give the exact geometry of the exact position between each speaker, how far they are apart from each other in millimeters, forward or backwards, vertical and horizontal. So all the axis, up and down, side to side, and back to forward, all the measurements are done in the simulation. And then after that, with these frequency response measurements, it'll tell you at a certain distance in front of it, you give it an exact simulation location. It'll tell you how the waves sum together in the free space and what the frequency response will be at that frequency at that exact position. So that's kind of the procedure we use to do our simulation, and then finally we go through our testing, which happens outside in the vehicle, which is our test location. I'm Johnny from the Speaker Building Garage. Hello, I'm Johnny from the Speaker Building Garage. So this is the final part of our series here. We're going to wrap up this entire video production with a short little demonstration of what happens. So we were before in the Speaker Building Garage. So now I'm in the testing location, which is inside of a Toyota minivan, a Sienna 2002. This is where the speaker is installed. This is where it's designed to be operated, and this is where we test it. So this is our testing room where we do our testing and our tuning, both with software and by ear. So I'm going to give you a brief run over of how this actually works. This is very interesting. Down here on the floor we have power inverter. You see that thing down there at the bottom? That 2,000 watt inverter. What that does is it takes electricity from the battery and turns it into AC 120. So you have 3 outlets down there, just like you have in a house. So you can plug in anything that needs to be plugged into an outlet. That big power amplifier, this item right here, this is a QSC power amplifier GXD8. It is Class D, very efficient, and it produces 3,400 watts of power at full power into a very low impedance. Now obviously I don't use that much here because you need to put several speakers on both the right and left side to get that power. But even for an application like the car, it produces a very large amount of power, minimal heat, because it's Class D amplification, which is like 90% efficient. So the way this system works is you have an MP3 player. That's where the signal comes from. So that's an MP3 player like you would put in your pocket, you take to the park or whatever. So it plays all kinds of files, like music files. You can play any song you want in there. It has a plug for headphones. That's that black jack right there. That jack goes under here through gold-plated monster cables or signal transfer cables underneath the seat. And right here there used to be a cup holder. This side still has it. You put your cup in there. I removed it from this side and built this little box, and the cables go inside there, and there's a volume control. And this is how I control the volume of the system. So the signal first comes from the MP3 player or the file player. It goes into the volume control box. We regulate the level, and then it sends that regulated level through another cable into our amplifier. The signal leaves the amplifier and goes to the crossover board. And this other speaker on this side has its own crossover, which is under the seat, because I'm not working on this one right now. I only build one box, and once I perfect it, then I'll make a copy of it, because I already know how it works, because this one will be a copy of that one, the same thing. This one here has a crossover, but it's a generic one from the store. It's not like really good. It's just there so I can hear a little sound from it. The one that we're testing and working on is this side. So the crossover circuit that controls, like we talked about earlier, the frequencies that go into the woofer, the mid-range, and the tweeter, is this one right down here. You can see the same components we saw in the garage. Inductor coils with the red wire, The little purple ones are and the black one, that's capacitors, and here's the resistors right here. Now the reason why this circuit is designed this way is this is a testing circuit. What that means is instead of soldering the components on the circuit board into a permanent configuration, we create a board like this where we're using terminal strips. See the terminal strips? And basically what a terminal strip is you can undo the screw right here. This is what it does. You undo the screw and you can connect a wire to it. So they use this in all kinds of electronics. These are nickel-plated brass terminal strips. So I've soldered the wires into the proper circuit configuration. So the sound enters, signal enters here. It goes through the capacitors, to resistors, and over to the output of the tweeter. For the mid-range, it enters here, and another branch goes through the coil, through a capacitor. That's that bandpass I talked about earlier, which controls a narrow range of frequencies that go into this speaker. And then for the woofer, which is the big speaker here, we want only the low end, and when it goes higher, we want it to start dying off so that it can transition over to this one. So it goes to a coil right here. In this case, I got two because I want to get a certain value, so I had to add them together. It goes through this coil and that coil, and it comes out and it goes through here, over to this, down to here, and it goes into ground. So this is the first part of the two-order circuit, second order circuit. It goes to the coils, and from here it goes right into the woofer, and then a parallel leg goes from here to ground through these capacitors. So the way the circuit's configured is we have a second order circuit, a second order low pass filter for the woofer. We have a first order band pass for the mid-range, and we have a first order high pass with attenuation resistor network for the tweeter, because the tweeters are louder than the rest of the system. This plays around 100 decibels per watt, this 100, and that's 110. So if you just put them the way they are without making the resistors in this place to kind of lower the sound, then the high frequencies, the bright sharpness, it'll make too bright and too clear, because this speaker is more efficient than these, because these are direct radiators, and this speaker here has a little tiny diaphragm. This is a horn. So whenever you put a speaker on a horn, like this shape, a horn in front, it amplifies the sound. So speakers that are mounted onto a horn are called a compression driver, because the diaphragm that's in the back is at the very back of the horn, and just like when you blow on a horn or talk through a horn, the sound gets louder. The horn amplifies the sound. It does what's known as acoustic coupling. And that's another topic we'll get into on a different day. Totally different topic. I'm not going to get into that right now. Someday we'll talk about acoustic coupling. So anyways, that's how this system works. This is the crossover. So if you want to change parts, if I want to change this, is 3.9 microfarads. If I want to put a different capacitor in here, all I have to do is unscrew it, and you'll see what happens. When I unscrew the screws on this, it comes out. Now, if you solder the parts permanently, you can't do that. So this is an adjustable circuit. That means every single part that goes in here, you can change it for a different one, so you can keep changing the circuit to alter the sound, and that's how you experiment. You make your measurements, you make little changes to the circuit, you think, what would happen if I add a little bit more capacitance? You put a bigger capacitor, and you listen to the changes and take notes, and you keep refining it like that, and that's how you tune a speaker. Every company in the world does it. Bose Audio, Polk Audio, Dyne Audio, those multi-million-dollar, I'm exaggerating, but you know, they cost thousands of dollars, high-end, like home theater audio systems that wealthy people have, all the way that level, all the way to like the average Pioneer and Walmart. Every single company that makes a speaker box or any kind of speaker they sell, they go through a process where they take measurements and they do testing with actual components and listening to determine how that's going to work. Some cheaper things, they just all do it in the software. But better quality speakers, the acoustic engineers like myself, actually run audible tests using configurable circuits like this, where they can adjust the parts to determine what effect that each change they make by changing a component here will have on the speaker, and they listen to it, and then they make more changes, and it's kind of like fine-tuning an instrument or making a beautiful painting. You add a little bit of something, then you change something else, and you watch to see what that does, then you change something else, and you keep adjusting it in little increments, and you keep changing little things, and you make it get better and better until you finally have something that's really nice. It's a project like this can take months. I've been working on this for 5 months. That's not unusual, because some of the big companies that produce high-end audio will work on 1 year to 2 years before they finally have products they can release and sell in the store. So it takes a long time to develop a product. But that's what I'm working on right now. So, and then you want to put the capacitor back in, see it's loose. If I want to tighten it up so I can use it in the circuit, I just turn the screws with a screwdriver like that. Now that I've turned the screws, now it's stuck in there. See what I'm saying? So any one of these parts, I can remove it. These ones here, I just pull the clip and it comes out. So none of these parts are permanently connected here. They're just temporarily screwed down. So any single part you see, this one, that one, this one, any part, could be replaced with a different part with a different electrical characteristic that will have a different effect on the sound. And by trying hundreds of parts and looking at your measurements in the software and then trying the parts and taking notes, you continue this process of tuning and adjusting the sound until you get it to sound really nice in the place where you intend to listen to it. That is how every audio engineer in the world that works for a major company that produces audio equipment like loudspeakers, that's how they designed the QSC K12 series. That's how they designed the Yamaha. So every piece of speaker, every piece of equipment you've ever seen as a loudspeaker that they sell in the store, it was designed by an engineer like myself that works for an audio company, and they go through these procedures to develop and design their product. So that's how it's done. That's how the system works. We got the speaker here, and we got the speaker there. We got our software right here. In a moment, I'm going to do a short video demonstrating. I'm going to do a live demonstration of exactly what we use with our tones and our pink noise, and how we use this small test microphone, which is a high-end microphone designed to capture a flat frequency response and give us measurements that we can see on that screen, and that will guide us in knowing what part of the sound spectrum is too high, too low, and then we can do more tests and use our ears to fine-tune it some more. So anyways, that's it for this part of the video. The very last part here we're going to do next is going to actually be a live demonstration. So don't stop at this point. Don't turn it off. Don't get bored. It's not going to last that much longer, but I promise you the next little segment is going to be very, very interesting. I'm actually going to show you exactly how I use this microphone and this advanced software here to make measurements inside this vehicle of this speaker, and I can see them on that screen, and that is going to guide me and tell me what I need to change. I'll see places that are higher, places that are lower. I'll see what effect it gets by moving the microphone to the left, right, like when you move your head, when your ears move. It's going to tell me a lot, and then I can go down here, and if I see something I don't like, I can start making changes. I can come back in a few days and add a part, make a little adjustment to the circuit, listen to it, and then I think I got a good design. I go back in the software, I take the measurements, I do more calculations, and I keep going forward. Anyways, this is Johnny from the Speaker Building Garage, and the very next part of this video, the last part, is going to be the most interesting part. Is actually going to be a live demonstration of how we actually test using the software, this speaker, in this environment. Johnny from the Speaker Building Garage. Okay, so this is Johnny from the Speaker Building Garage. So I powered up my amplifier. It's on now. Hear that hiss coming from there? Speakers are going. We're powered up. Computer's on. Let's get right into it. So this can be quick but very interesting. So here's the software we use. It's called Room Wizard. It's an EQ software, but it has many functions of different tests. So we're going to run the test right now. We're going to get into real-time analyzer, which shows frequency spectrum. So this one here you can also use to listen to like human vowel sounds and like chart the frequencies in the human voice for learning vowel tones, how the tongue affects sound. You can use it for applications like determining different sound patterns and languages, how to improve accent. This is amazing technology. I'm going to have another video later that talks about the human voice, language learning. I'm going to get deep at a level most people never even heard about into this subject. So anyways, let's get started now with the real-time analyzer. And here's the test microphone. I'm pretty sure it's up and running. We're going to turn this on the side over here. And there's a button. It starts it. Testing 1, 2. See the lines coming up? It shows the exact sound pattern. So I'm going to put, so I don't think I won't do peak. I'll just do spectrum. So I'll do an example of vowel sound. Ah. See where the peaks are? Ooh. They're different. Ah, ah, ooh, ooh. So for every sound, it shows the exact distribution of energy. Right now, ooh, it changes. You can see the peaks. And now I go quiet, it'll go down. So what we do is we use pink noise. And pink noise is like a static sound, but it has an equal amount of energy. So basically when you hear noises that don't have tonal quality, let's say you hear a noise that sounds like static. The reason why it sounds like that is because all frequencies are together, but they're in no particular mathematical order, so you don't hear a tone. That's the secret. There's no one dominant frequency. There isn't a harmonic series. You have all the frequencies all together, all of them, every possible tone, but it's all random, and they're not in any particular order. It sounds like static. So static is all frequencies energy equal. It's equal energy across the entire audio spectrum, not just at one frequency, which your ears perceive as a particular a tone, as opposed to which just sounds like noise. Has all the frequencies too, but the difference is they're randomly arranged as opposed to it's just one frequency. So So you see the difference. So the bottom line is when you're working with this stuff, you need a random signal source, we use pink noise because it has an equal amount of frequency energy randomly distributed per each octave. So it approximates the random distribution of energy and live acoustic sound in the environment. So what we're going to do with the pink noise test is we're going to play that through the speaker, hold the microphone in front, and see how it produces different energy level at different frequencies. So I'm going to start that right now and put the microphone on the side. The computer is ready to go, so I'm going to turn on a sample test from my player here of pink noise, which is static. You're going to see the lines forming on here. It's going to show the distribution of energy across the audio spectrum. So as you can see, by changing the position of the microphone, which is like represents where your ears would be, where you're listening from, depending on the reflections coming off the different surfaces, the sounds add together, and the amount of energy you see across there, the pattern changes. And that tells us something like we saw it was really high here. Like I put a peak here, it'll hold the peak or the highest level, and it'll record that. So if I put peak, I'll click that button. Now it'll show the highest level we're going to get when we turn this up. It's frozen. The red line shows it. See how that, now we froze it in time. The black line was moving. It shows a live demonstration of how it sounds as it's moving right now. We record a permanent demonstration. We have a permanent sample right there. We froze in time the peak reading. See how it's louder here, a little weaker there. It has a peak there and it goes down depending on the position of the microphone. When you place the microphone in the position where you're going to be listening to the sound, it'll be telling you about the spectral energy at each frequency along this here. And the frequency go this way gets higher and go that way gets lower. It'll show you what the level is at each frequency range. And you can compare that and see how it's affected by the reflections off the walls. The sound reflects off of this and bounces back. Everything affects the sound. It's the original sound comes from here, it reflects, and all that adds together. So that's how a pink noise test is done and how that tells us. The other kind of test that can be done is called a sweep. And that's a single tone. Let me see if I can get it out here. It's called, it's one tone that starts really low and goes from there all the way up. So now I'm going to see if I can find that in here. I know it's somewhere. I have a very long list of test tones in this device here. And it's got to find the one that is the sweep. That goes from like 10 hertz or whatever. And it goes all the way up. There we go. So here's what a sweep sounds like. It's totally different. Let's turn this up. You can hear the tone coming up. Now we're going to try to get a little louder so we can see it on the screen. And that's not that part. So we'll move it over this way so we can see what we're doing. Let's move it this way. See that black peak there? That's the dominant tone we're hearing right now. It's coming up. See how it's rising right there? That big peak, that spike right there. Put the microphone in front. The microphone is listening. The sound spectrum's changing, see? Put it closer. That big peak. See it rising there? It's going higher. Place the microphone over here. See, it's going up right there. See? And this shows some background static and sound. This peak here is the main tone right there, the dominant frequency. You can see a big sharp rise right there. It's going up. So there you have it. It keeps going farther and farther, but I'm not going to go away. And you have a general idea how it works there. So whatever tones you're hearing or whatever distribution of energy you're hearing, it's represented right here. In other words, what that means is whatever energy you're hearing is going to be showing that distribution of energy on this screen right here. And that's going to be telling you stuff about your sound. And so when you run these tests, if you want to record it, you get a line like this. The black line is moving while I'm talking. See, it's responding to all the frequencies of my voice and showing you where the dominant places are. And the red line is a permanent recording that shows you how the highest level we got to for that whole thing. So you see the graph going all the way across there. That is how the system works. We use software like this, test microphones like that, and we play tones and static through this speaker to make measurements. After we make the measurements and we see things we want to change, we make adjustments here, we sit in this chair and we listen. We don't like the way it sounds, we make more adjustments here and we keep tweaking it until we get it exactly the way we want it to sound. This is Johnny from the Speaker Building Garage. Thank you for watching.